In example 2, we want to figure out how many solutions each system has. We have A, B, and C. Let's look at A. First we see 2x plus 6y is equal to 18. The second equation, if we're going to try this with linear combination or elimination, we've got to have one term exactly opposite the other term, which we don't have. What we could do though is multiply this whole bottom equation by -2. I'm going to write the top equation down, and then I'll write the other manipulated equation here. So we're going to multiply each term by -2, so that's -2x minus 6y is equal to -18. Now we're going to add these together. That's 0, that's 0, and we have 0 on the right hand side. Notice here that both variables are gone. We don't have one variable to solve for, and we're left with a true statement. 0 does equal 0. This is true, which means there's infinitely many solutions. And this asks us to identify how many solutions does each have, and even if it doesn't, if it just asks you to find the solution, you're going to write infinitely many. Think about it. If we multiplied this by just 2 instead of -2, we'd have 2x plus 6y is equal to 18. That's the exact same equation as the one above it. Because it's the exact same line, whatever works for one will work for the other. And there's an infinite number of points that work for just one line, and if it automatically works for the other, well, there's an infinitely many number of solutions then to this system. Let's try it with this one over here. Right now, I can see my coefficients are pretty good, but I'd like to change this one right here, and I'd like to make each one of these signs opposite of what they are right now. So we'll multiply that by -1, and I'm just going to write down that first one here. It's up to you whether you want to do that. I just think it helps keep me organized. And we're going to multiply this entire equation here by -1. So we've got 2x minus 5y is equal to -12. At first glance, this might look like the same equation if we only look to the left of the equal sign, but it's actually not. Let's see what happens. So -2x and 2x is 0, 5 minus 5y is 0, 7 minus 12 here is -5. Here again, both variables have gone away, and we're left with a statement. This statement happens to be false. 0 does not equal -5. So what this means, maybe I should write an arrow here like I did in the last one, this means that there is no solution to this system of equations. If you graphed each one of these, you'd find that they are parallel lines, but definitely not the same line. Because parallel lines don't have an intersection, there will be no solution to this system. Let's work with the one on the bottom. This one, I think it's going to be most useful to multiply the bottom equation by -4. I'll write the top equation down. So that one's right here. And we'll write this other equation right here. Let's see, -4 times -2, that's 8y. And then we've got a -20 here. Okay, so 12x minus 12x is 0, -8y plus 8y is 0, both variables have gone away, and 20 minus 20 here is also 0. Now it doesn't have to be 0 is equal to 0, that happens a lot though when you do elimination like this, but if you did something else and you got 5 is equal to 5, well that's also true. So the key here is not 0 equal to 0, but determining once the variables have gone away is the statement you get true or false. If it's true, then you have infinitely many solutions. If it's false, like this one above, upper right hand side there, then you're going to wind up with no solution. But this one's definitely infinitely many.